All right, welcome back, everybody. We've got another 3 talks with a heavy focus on rotorcraft. We're going to start off with another one of our international liaisons, and like last time, it'll be a pre-recorded talk, and then hopefully we can get them on Zoom and then ask some questions. So the first talk is by Etienne Parizet from INSA de Lyon, a longtime corporate liaison with the CV, and he, last I checked, actually runs the Acoustics and Vibration group out there. And he's going to talk about the effects of vibration and sound on comfort in rotorcraft.
Hello from Lyon. I would have liked to be at Penn State for this presentation, but the situation is a little bit complicated. Thanks to Steve and the organizers of this workshop for allowing remote presentations. I work at INSA Lyon. INSA stands for National Institute of Applied Sciences, an engineering school that trains about 1,000 students per year. I work in Laboratoire Vibration Acoustic. The lab has 14 permanent researchers, around 28 PhD students, and the research areas are organized in 4 parts. First of all, vibroacoustics, a topic on which the lab has built its reputation. You may know my colleagues Laurent Maxit, Nicolas Totaro, Kérem Ege. Laurent works about sound radiated from submarines, as you can see here, an example of his work. And this topic, of course, is a little bit painful for us in France, especially in front of an American audience. And Nicolas and other colleagues has developed a method in order to simulate complex sound fields over a plate or another structure, whether single loudspeaker which is moved around above the surface. They can simulate a diffuse field or a sound field due to a turbulent boundary layer. Our second topic is about source localization and inverse methods, to which Jérôme Anthony, who is currently the lab director, or Quentin Leclerc contribute. An example of this work is shown here. There was a benchmark organized by the German Institute DLR in order to localize sound sources on the tail of a plane located in a wind tunnel, and they were able to localize very small sound sources. A third topic is non-destructive testing, using different techniques as ultrasounds or X-ray tomography or structural health monitoring. And finally, noise and vibration perception, but I will give an example on the studies we do in that field. We have some facilities, a large reverberation room and a large semi-anechoic room. We also have a soundproof booth in which our listening test experiments are conducted. You see here the room is just behind that door. Not too easy to come in, as some very important renovation work are conducted in the building. This has created some trouble this year, but should end in December. Inside the room, it looks like that. And finally, I will mention that the lab is one of the many teams in Lyon specialized in acoustics. You may know colleagues in LMFA, LTDS, LAMCOS. Altogether, this represents around 19 people working in acoustics. And this is the most important research group in France. And we received a lot of money 10 years ago from the French government to increase the collaborations within this network. I just would like to mention that we have some funding to host foreign researchers and students in our teams, or to help our PhD students to stay in foreign teams for some months. So this is a way to increase the collaboration between you and us. Let's go to the topic of this talk, discomfort due to noise and vibration in helicopters. This study was conducted by a PhD student working for Airbus under my supervision. And the topic was comfort for passengers of helicopters like this one. And you certainly know that in helicopters, sources create noise and vibration, which really contributes to the uncomfort of passengers. Helicopters are complex machines, and vibration measured in helicopters exhibits this kind of spectrum. You have very strong frequencies due to the rotation of the rotor multiplied by the number of blades of the rotor. You also can detect some vibrations due to the tail rotor and some other vibrations in the very low frequency range due to the dynamic of the helicopter. Regarding noise, it's also very complex. You see the signature of the main rotor, the gearbox, the engine, plus wind noise. So altogether, a lot of vibration and noise. And the research question was this one: can we evaluate this discomfort from measurements? We work about the evaluation of discomfort due to noise only, and then due to whole body vibration only, and finally about the contribution of noise on whole body vibration to overall discomfort. But before we start, I would like to mention a few things. We can talk about discomfort or annoyance, which are slightly different. Comfort is related to well-being, relaxation, and can be evaluated by self-assessment of people. Annoyance is more related to an activity. You can ask people to do a task and measure their performance, or you can also ask them to evaluate how much they were annoyed during this activity. The second choice we have to make is in situ or laboratory experiment. In situ experiments, of course, are the more realistic ones, but the big issue is to control the stimuli. On the other hand, laboratory experiments allow you to control the stimuli, but the ecological validity is a little bit more complicated to be ensured. Also, are people exposed to stimuli during a short time or a long time? If you want to measure performance, a long exposure is necessary in most cases. If you ask people to evaluate comfort or annoyance, the exposure duration can modify the results, but only to a little extent, as you can see on the figure. And final issue is about subjective evaluation, self-assessment as I mentioned, or physiological measurements. Many people prefer to measure some physiological data like heart or respiratory rate, electrodermal activity. We don't do that because I think that, first of all, it's complicated. And also, most importantly, the physiological measurements are not related to noise annoyance. This can be seen in the literature, or hardly related, as reported by Wolfgang Edermeyer in a recent paper. So, to conduct that research, we decided to conduct laboratory experiments using self-assessment of discomfort by people and during a short exposure. First of all, let's come to the evaluation of noise discomfort. We recorded 45 stimuli in helicopters, recorded in different cruising conditions, and the level was limited to 19 dBA because, of course, noise can be very loud in helicopters, but we didn't want to submit our participants to too high noise levels. The experiment took place in Airbus, in Marignane. You see here the listening room. They used four loudspeakers around the participant who is seated on the chair here, plus two subwoofers because the level is very high in the low frequency range. 33 people participate to the experiment. There were employees from the company. And after the presentation of each sound, people had to evaluate the discomfort using that scale, which is standardized. That scale is going from a little uncomfortable to extremely uncomfortable. The results are very simple. It appeared that loudness, for example, computed according to ANSI S34 standard, which is now ISO 532.2 standard. This model proved to be an accurate predictor of discomfort. It was much better than a weighted level, overall weight level, or anything else. Of course, there are very large differences in loudness in our stimuli. The ratio is around 2, so that we know in such cases loudness alone is enough to describe the annoyance of sound. In case of smaller differences, we should take into account some more subtle timbre differences. You see here the discomfort as predicted from loudness values and the discomfort measured or reported by participants, and the correlation is quite correct. So for sound, things are easy. Loudness is a good predictor of discomfort. For whole body vibration, the situation is a little bit more complicated. We conducted two experiments. In the first experiment, we wanted to evaluate the exponent of the Stevens law, which relates the physical level of a stimuli phi to the associated sensation psi through a power function. This is widely known in psychophysics, and the value of the exponent is also quite known for acoustic stimuli, for example, but for vibrational stimuli, you can find in the literature many different values of alpha. So we wanted to make our own experiment in order to determine these values in the frequency range corresponding to the main excitation in a helicopter, which is due to the blade passage frequency. So it's the rotational speed of the rotor multiplied by the number of blades. In that experiment, we used a bench developed many years ago in the lab. It's a platform here suspended on 4 springs and moved by a shaker. The limitation of the system is that the lowest frequency is around 2.5 Hertz, but it's not a problem for our application. We fixed a helicopter seat on the platform, and we submitted people to 41 sinusoidal signals whose frequency were between 15 and 30 Hertz. The procedure was a magnitude estimation one without reference. Each participant was submitted to the 41 signals, but each signal was repeated 3 times in a random order. And 53 people participated to that experiment. There were INSA students. One main advantage of being at INSA is the number of students, and they are all ready to participate to our experiments so that we can really conduct experiments with many people in a very easy way. The results are as follows. First of all, we had to normalize individual results. following a procedure which was proposed by Anne and colleagues. You see here the example of individual results at 20 Hz. Each curve corresponds to a participant and represents the geometric mean of the 3 values he gave for the 3 repetitions of each stimulus. So there is a large scattering between all individual results, which is mainly due to the way people use numbers, because in a magnitude estimation procedure, they can give any number corresponding to their sensation. In order to reduce this variability, we computed the individual answer and the general answer of the panel, and you just subtract to this value the average answer of the participant, and you add the average answer of the panel. By doing so, you get this set of curves here, and the variability is much lower. The average evaluations are represented here. You see on the x-axis the acceleration level of the stimuli. Each symbol corresponds to a frequency, and the y-axis represents the evaluation in a logarithmic scale. We found that Stevens' law is, of course, respected, except that kind of saturation effect appears at high levels. And the evaluations are frequency dependent. The lower the frequency, the higher the discomfort. But if now the physical level are expressed in velocity, you see here that the frequency dependence disappears. So discomfort in that frequency range is related to velocity, and this is in accordance with the frequency weighting proposed by ISO 2631 standard. In that frequency range, the frequency weighting has a slope around close to -6 dB per octave, which correspond to the transformation we made from acceleration to velocity. So we could evaluate the exponent of Stevens' law, which can be different in the in the range of low levels as compared to the high level range, and this had been mentioned many years ago by Miwa. Stevens' law exponent depends on the level range in the case of vibration, whole body vibrations. So this study is published in the Journal of Low Frequency Noise Vibration and Active Control. If we want to evaluate discomfort due to vibrations in a rare and complex situation, we can use ISO 2631 standard. It consists in measuring triaxial vibrations at the feet, the seat cushion, and the backrest using this kind of device, then applying a frequency weighting for each accelerometer and each direction according to a set of weighting curves, and then computing the root mean square of all weighted acceleration. And this value corresponds to a level of discomfort. In order to check the validity of the standard in our case, we conducted 2 experiments. The first one used vertical vibrations only on the test bench I presented before. The second one used triaxial vibrations, and for that experiment we used a device, a test bench, which is installed at Airbus. And you see here the test bench, it's named the Cube from Team Cooperation, and there are 6 actuators in the cube. In order to move it in any direction, you can also rotate the cube. Theoretically speaking, it can do anything. In a practical point of view, it's very complicated. and you have to adjust the signal before and then to check at any time that the system is really doing what you want it to do. So it's very complicated, but you can, using this device, really simulate triaxial vibration. In this experiment, we use 75 stimuli really recorded in helicopters, and 30 people participated to that experiment. In both experiments, people were asked to evaluate the uncomfort of the situation using this scale. And we also, at the same time, we measured the vibrations at the feet of the participant, on the cushion and on the backrest, in order to know the exact level of vibrations submitted to the participant. Because, of course, depending on the participant, his mass, his body size, the seat transfer function can be modified, and the vibration really exerted on the participant can be different from one people to another one. It appeared that the standard correctly predicts discomfort. You can see here on the x-axis the uncomfort index computed according to the standard. On the y-axis shows the mean discomfort evaluations given by participant. So the relation is strongly linear. The determination coefficient is quite correct, but this prediction can be improved. You see here some stimuli for which predicted discomfort is very different from the real one. We try to improve this evaluation, this prediction, by taking into account amplitude modulation of signals. It appeared that some stimuli are amplitude modulated. So we propose to detect the modulation amplitude and to multiply the signal by a coefficient which is 1 plus the value of this modulation amplitude. We do that, and then we run the ISO standard as it is defined. This is a very slight modification of the standard. And this modification allows a better prediction of the discomfort. As you can see here, the points are much closer to the regression line. The determination coefficient is higher. So the conclusion of these studies is that taking into account amplitude modulation can really improve the predictability of this standard in the case of helicopter vibrations. So this study has recently been published in Ergonomics. The final part of the research question is related to contribution of noise and whole body vibration to overall discomfort. In the previous experiments, we focused people on noise or vibration, but now we will ask them to evaluate overall discomfort. In that field, several models have been proposed. You can find them in the literature. Most of them are linear. So the overall discomfort, psi, is a linear combination of specific discomfort due to vibration or due to noise. Some example of papers here. Dempsey on leather roads were people working at NASA many years ago. And they used that kind of simulator. The experiment was a very complex one. Also, you can find in the literature some nonlinear models taking into account an interaction between noise and vibration, as proposed by Howard and Griffin. This study was related to noise and vibration due to train, as far as I remember. Or some kind of quadratic mean of specific discomfort as proposed by Aladdin and colleagues or one on Griffin in one of the latest papers from Griffin. For that last experiment, we used 54 stimuli recorded in helicopters in different cruising conditions. The playback was ensured by the cube at Airbus for vibration, and sounds were presented through headphones plus 2 subwoofers. 32 people participated to that experiment, and they had to evaluate the overall discomfort using the same kind of scale. It appeared that the overall discomfort can be represented as a linear function of specific discomfort due to noise, D noise, and specific discomfort due to vibration, D vib. D noise is computed as a linear function of loudness, and D vib is the function of the modified ISO index I just presented before. The relation between predicted discomfort and measured one is shown here, and you see that the relation is strongly linear with a very high determination coefficient. But the relation can be improved once again, and in order to improve it, we added that interaction part here, which is the difference between the two discomforts due to noise and due to vibration. It means that the situation must be balanced between the two sensations. If you add this third term, you really improve the description, the prediction of discomfort. As a conclusion, I would say that loudness and ISO index are useful predictors for specific and combined discomfort due to noise and vibration in helicopters. ISO standard can be improved by taking into account amplitude modulation. And the important thing is that overall discomfort also slightly depends on the balance of specific discomfort. Thank you very much for your attention. I hope that we will be able to meet for real in the next future. I wish you a fruitful workshop. Have a nice day. Bye.
Okay, we're going to attempt to transition to Zoom again and hope we see Etienne. Meanwhile, I'll think of questions. I'm hoping our rotorcraft people have some questions about that, because that was a neat study. Bonjour, Etienne. Can you hear me?
Bonjour, Steve.
Ah, wonderful. Thank you for the great talk.
Hello, everyone.
Thank you for the great talk. We very much enjoyed it. And we've got a room full of people here, and we're going to see if there are any questions about the work. And I've got a microphone that I'll hand around. So I'm going to Ed Smith, who runs our rotorcraft group.
Okay, bonjour, Etienne. We enjoyed your presentation, and it's good to see INSA working on this problem. I'm wondering if you and your group came across a couple of other studies. I know when I was at CeLyA a number of years ago, they were also looking at this similar problem, especially from the acoustics point of view. They had a room full of recorded sound signatures from some of their commercial helicopters, and they were looking at annoyance levels. I was wondering if they perhaps published any reports in that area from the Italian side.
No, I don't know. I don't know any publication about that work.
Okay. I know there's another one on the vibration side. The U.S. Army has something called the Vibration Intrusion Index. I may be able to get you, there are some publications related to that. For the military helicopters, they try to weight the different vertical and longitudinal and lateral vibration levels. So that one, if you're not familiar with, that's on the vibration side, not the acoustic side. Just let me know and we can get you that information.
Oh yes, that would be very, very interesting indeed. I think they are interested in very high levels of vibration because this can prevent people from doing their task in a correct way. So I guess the levels are much higher than the levels we are interested in. But if you have some data about these studies, I would be very interested in, indeed.
Okay, thanks.
Okay, other questions?
In one of your last slides, I think you had this combination of noise and vibration discomfort, and you said you had improvement with the last term, the noise minus vibration. I'm just wondering how much improvement, like how much your R square improved there? The prediction.
I have to go back to my presentation because I don't remember the answer.
I think it's like the second from the last.
I think it was presented. Yes, because without that interaction term, the determination coefficient was 0.76. And if you include that interaction term, it goes to 0.87. So a slight increase.
Okay.
In accuracy.
Okay. I have another question. So at the beginning, your limiting factor for the noise was the dBA metric for your subjects. I'm wondering, this is more interior noise and vibrations, not the environmental. Why are you using dBA but not an SIL metric, speech interference level?
We use dBA because it's a very common metric to limit noise exposure. You know, if I don't know in your country, but in France and in Europe, dBA is used to define the maximum noise exposure during a working day, for example. So it seemed natural for us to use this metric to limit the overall level of sounds to be presented to subjects of our study.
Okay, thank you.
Okay. I think that's about all the time we have for questions, but thank you so much, Etienne, for your time doing the pre-recording and being here now. And we certainly hope that we can see you in person sometime in 2022.
Thank you for your invitation and have a nice workshop. Goodbye.
Okay. Au revoir. All right, so carrying on with our rotorcraft theme this mid-morning. Next up is Ed Smith and also Dr. Eric Greenwood, and they'll talk about the work going on in our rotorcraft center. Microphone's up there, and there's a clicker.
All right, good morning, everyone. It's always